We keep asking the wrong question about the moon. Everyone asks, can we go? And we already know the answer because we did. 12 people walked up there, but almost nobody asks the harder one. Can we actually live there? Not visit, not plant a flag and leave. Stay for years, for a lifetime. Because the moment you try to answer that honestly, the glowing dream in the sky starts to look less like a home and more like a trap that closes slowly. So before you ever dream of calling the moon home, let me walk you through what living there would truly cost. One hazard at a time until you see the full picture. Now get yourself comfortable, hit subscribe, we begin. Let's start with the fantasy, because the fantasy is powerful and it is old. A glowing second home hanging in the night sky. A place we could reach in 3 days. For most of human history, that was all it could ever be. A light to steer by, a face to tell stories about. But that has changed. Right now, this decade, space agencies and private companies, and some of the wealthiest people alive, are pouring fortunes into a single idea. Not visiting the moon, but staying, building, living there, permanently, for the first time in the history of our species. And the pictures they show us are beautiful. Silver domes under a black sky, gardens glowing behind glass, a frontier, calm and waiting. But the postcard lies. The moon is not a frontier. A frontier is hard, but it wants nothing from you. The moon is something else, a place where the environment itself is set against the fact of your being alive. Every hour you spent standing on it, forces you cannot see or feel would be working, patiently, to end you, in ways this planet never prepared you for. And to understand all of them, we have to understand the first one, the one that everything else grows out of. Here is the strange part. The thing most likely to kill you on the moon is not something that is there, it is something that is not. The moon has almost no atmosphere, not thin air, almost none at all. Scientists don't even call it an atmosphere, they call it an exosphere, which is a polite word for a scattering of stray atoms so sparse they rarely ever touch each other. Let me put that into something you can hold in your hand. Picture a single sugar cube of air. 1 cubic centimetre, the kind of volume you breathe in and out without a thought. Down here at sea level, that little cube holds somewhere around 100 billion molecules, jostling shoulder to shoulder. On the surface of the moon, that exact same space holds roughly 100, not 100 billion. 100! You could almost count them. That is not a thinner version of our sky. That is, for every purpose that matters to a human body, a perfect vacuum. And here is the detail that should make your skin cool. Down here on Earth, our most advanced laboratories spend enormous effort building ultra-high vacuum chambers, sealed steel vessels, powerful pumps, baked for days, all to create a pocket of emptiness that rare. On the moon, that emptiness is not a hard-won achievement locked behind reinforced walls. It is simply what is outside. It is the weather. So what does that emptiness actually do to a person? This is where the calm ends. Strip away the suit, and the pressure holding your body together vanishes. The gases dissolved in your blood, and the water in your soft tissue no longer have anything pressing back on them, and they begin to expand. Not an explosion. The movies get that wrong, but within seconds, the moisture on your tongue would start to boil. Your tissues would begin to swell, and the oxygen your lungs were built to pull in would instead be dragged violently out into the void. Your brain, starved, keeps working for a moment on the oxygen it has left. 15 seconds. That is the window. 15 seconds of dimming, useful consciousness before the lights go out. And we are not guessing at this. We know it because one man lived through it. In 1966, a NASA technician named Jim LeBlanc was inside a vacuum chamber testing a spacesuit when the hose feeding him pressure came loose. In seconds, the pressure around him collapsed toward vacuum. The last thing he remembered before consciousness left him was the saliva on his tongue beginning to bubble. He was out in roughly 14 seconds. Rescuers rushed to repressurize the chamber and reached him in time, and he survived. But that number is the one that matters. 14 seconds. That is all the warning a human body gets. After that, unconsciousness. Then, over the next couple of minutes, the end. Think about that for a moment. Not hours, not the slow death of cold or hunger. 15 seconds between a working mind and a closing door. Every other danger on the moon, the cold, the radiation, the dust, the strikes from the sky, every one of them ultimately flows from this single absence. No air to breathe, no air to hold you together, no air to burn away what falls. Remove the air and everything else follows, which means a home on the moon cannot be a home in any way you have ever known one. Every structure up there has one job before it has any other. Hold one atmosphere of pressure inside against total nothing outside. And that difference, the push of ordinary air trying to escape into the void, is relentless. It leans on every wall, every weld, every seam, every pane of glass, every hour of every day forever. It never rests. It never weakens. So the thing they build on the moon is not really a building. It is a pressure vessel, a container whose entire purpose is to survive a difference in pressure. And the closest thing we have to it on Earth is a submarine. A submarine survives by holding the crushing weight of the ocean out. A lunar habitat does the mirror image. It holds the emptiness out and the precious air in. Same unforgiving physics flipped. But there is one difference that changes everything. A submarine can surface. When something goes wrong, it climbs back into a world full of air, where the crew can open the hatch and breathe. A colony's pressure vessel has nowhere to surface to. The air it holds is the only air there is. A slow leak, you might survive. If the sensors catch the falling pressure early, if there is time to find the crack and seal it. A sudden tear, you would not. Rapid decompression is not an emergency you respond to. It is an emergency that finishes before you understand it has begun. Down here, you have never once had to think about this. An entire ocean of air is pressing on you at this very moment. On your shoulders, the backs of your hands, your closed eyelids, and holding your body in perfect balance. Earth builds that wall for you, everywhere, for nothing, and it has never sent you a bill. On the moon, someone has to build that wall by hand, and then never, ever let it fail. And building it is where the trap tightens, because now we run into the cruelest arithmetic in all of spaceflight. Every cubic meter of space you want to fill with breathable air, you must first wrap in walls strong enough to contain it. And every kilogram of those walls has to be lifted off the Earth and flown 250,000 miles. Getting mass into space is staggeringly expensive. Even now, on the cheapest rockets we have ever flown, reaching low orbit, barely off the planet, costs something like $2,000 to $3,000 for every kilogram. Let me make that real. A 1-liter bottle of water weighs about 1 kilogram. To lift that single bottle just to the edge of space costs more than the bottle, the water, and the truck that delivered it, several times over. And low orbit is the bargain. Carrying that same kilogram all the way down to the surface of the moon costs dramatically more still. Now imagine paying that price not for one bottle, but for every wall, every beam, every airlock, every window of an entire settlement. The math does not work. It simply does not. And that impossible cost forces the designers toward one conclusion, the same conclusion reached by every desperate builder in history. Stop shipping materials in. Build with what is already there. The moon has one thing in endless supply, the grey, broken dust and rubble covering its entire surface, called regolith. Pile enough of it over a habitat, and it does three jobs at once. It shields against radiation, it insulates against temperature, and it adds the sheer heavy mass a structure needs to hold itself down and hold itself together. Mass you never had to launch because it was waiting there all along. But how you build with it, that is a fight the experts have not settled. One camp says, fly rigid modules, ready-made metal rooms, and simply bury them. Strong, tested, familiar, but heavy and cramped, and every meter of them stillborn on Earth. A second camp says, launch inflatable habitats, soft shells that fold up small for the journey, then swell into wide, roomy interiors once you arrive, giving you far more living space per kilogram launched. Lighter, larger, but a fabric wall feels dangerously thin with a vacuum on the other side. And a third camp says the real answer is to melt and print the regolith itself, robots fusing lunar dust layer by layer into solid shells grown directly on the surface, using almost nothing from home, rigid, inflatable, or printed from the ground up. Each solves one problem and worsens another. No one has proven which one keeps people alive across the years. The frontier does not even agree on what the front door should be made of, and while they argue, the surface keeps doing what it has always done. Because standing outside is not only a battle against emptiness, it is a battle against extremes this planet has never shown you. With no atmosphere to spread heat or trap it, the moon has no mercy in either direction. Under direct sun, the ground at the equator climbs to about 127 degrees Celsius, 260 degrees Fahrenheit. That is hotter than boiling water. Then the long lunar night falls, and the same ground plunges to around minus 173 Celsius, minus 280 Fahrenheit. Do the subtraction, and one single spot on the moon swings across a range of 300 degrees Celsius, more than 500 Fahrenheit, over one cycle. Imagine your own kitchen. Imagine the surface of a hot skillet and the inside of the deepest freezer ever built. Now, imagine one wall of your home being forced to be both, swinging from one to the other again and again on repeat. Here is the quiet damage in that. Different materials swell in heat and shrink in cold at different rates. Metal, glass, sealant, rubber. Each one grows and contracts by a slightly different amount. And a lunar day-night cycle takes about 2 Earth weeks each way, so every joint, every seal, every seam is stretched and squeezed on a slow, endless rhythm. You have felt this physics yourself. Bend a paperclip back and forth, and it feels fine, right up until, without warning, it snaps. That is metal fatigue. And on the moon, the sky bends every seal in the colony, back and forth for as long as the colony stands. And then there is what falls from above. Space is full of tiny debris, specks of rock and metal, most no bigger than a grain of sand, moving at speeds nothing on Earth prepares you for. Here, our atmosphere is a shield we never think about. Those specks slam into the air, heat up and vanish as shooting stars long before they reach the ground. That is what you are watching on a clear night. Our planet quietly taking hits for us. The moon has no such shield. Nothing burns up. Everything arrives. These grains, micrometeoroids, strike the lunar surface at an average of about 20 kilometers every second. That is roughly 45,000 miles per hour. A high-powered rifle bullet, by comparison, travels around 2,000 miles per hour. So these specks arrive more than 20 times faster than a bullet. And because the energy of an impact climbs with the square of the speed, a grain you can barely see carries the destructive punch of something vastly heavier. A dust mote with the bite of a bullet, and no warning, and no sound. We do have a defense, and it is clever. A Whipple shield, A thin outer layer held a small distance from the real wall. The incoming grain shatters against that first sacrificial layer and blows apart into a spreading spray, a cloud too diffuse to punch through the wall behind it. Think of a car's crumple zone. The front sacrifices itself so the cabin survives. It works remarkably well. But here is the problem a colony cannot escape. A shield protects one wall. A settlement exposes thousands of square meters, habitats, tanks, pipes, panels, vehicles, across not one mission, but decades. A study published in 2025 ran the numbers on a lunar base the size of the International Space Station. It found that such a base would be struck by something like 15 to 23,000 micrometeoroids every year. And the good news, the honest news, is that current shielding would stop very nearly all of them. The researchers estimated only about one impact every couple of decades might punch through. For one base, for 1 year, that sounds almost safe. And that is exactly the trap in the arithmetic. Because a colony is not one base for 1 year. It is many structures, for many years, across every exposed surface at once. And when you let a small chance run long enough, across enough walls, it stops being a small chance. It becomes a matter of time. The sky is not aiming at you. It does not need to. It only has to keep firing and wait. So look at what we are left standing in. A world with no air to breathe and none to hold you together. A wall that must be held against the void forever and can never once fail. A price for every kilogram that breaks the arithmetic of building at all. A sky that bends every seal until it fatigues and rains down specks that hit like bullets and never stop coming. And the strange thing is, there may be a single answer to almost all of it. Go down, bury the habitat deep beneath the regolith, or slip it into a natural hollow, and in one move you defeat the furnace and the freezer, and you defeat the rain from the sky. The dust that has been falling for 4 billion years becomes your armor. The frontier stops being a place you stand on. It becomes a place you hide inside. But burying yourself solves the walls. It does not solve you, because a body sealed under the lunar surface still needs two things the moon does not hand out to anyone, not to the rich, not to the bold, not to the first or the last. Air to breathe, water to drink, and a buried colony, safe from the sky, is only ever a few days of failure away from suffocation or thirst. So the question stops being, how do we keep the vacuum out? It becomes something far more urgent. In a place with no air and no water anywhere on its barren surface, where would the first breath and the first drink actually come from? The answer is hiding in the coldest, darkest places the moon has ever kept. So we go looking for that first breath and that first drink, and the search leads us to the strangest possible destination. Not the sunlit plains, not the gentle grey seas the old astronomers named, but the places on the moon where the sun has never once reached. Let's be clear about the problem first, because it is absolute. A human body cannot last more than a few days without water, and only a few minutes without air. And the moon, as far as anyone standing on it can tell, offers neither one freely. No lakes, no rivers, no wind carrying moisture, no open air of any kind. A settlement's very first task, before science, before industry, before anything, is to pull the two things that cannot live, without, directly from a world that seems to hold neither. And for a long time, we assumed the moon was bone dry. But we were wrong. Here is how we found out. In 2009, NASA tried something that sounds almost violent. They took a spent rocket stage, a piece of hardware about the size of a small bus, and aimed it deliberately at a crater near the moon's south pole. A crater called Cabeus, chosen for one specific reason. Its floor sits in permanent shadow, a place the sun physically cannot touch. The mission was called L-Cross, and the plan was simple: crash into the darkness, kick up whatever is hiding there, and read what comes flying out. On the 9th of October, the rocket stage struck the crater floor and blew a plume of debris up into the sunlight above, where a trailing spacecraft was waiting, instruments open to catch the spray. And in that spray, water, actual water ice, mixed into the lunar soil. The scientists put a number on it. In the material they measured, water ice made up around 5.5% of the mass, roughly 5 parts in 100. That may not sound like much, but hold it against what we expected. To grasp it, picture the driest desert you can imagine, the sand of the Sahara. That patch of shadowed crater floor was estimated to hold about twice as much water, by weight, as Sahara Desert soil. On a world we had written off as a dead, dry rock, we had just found frozen water hiding in the dark. But that raises an obvious question. How does ice survive on a surface that bakes to over 100 degrees Celsius in the sun? The answer is that it doesn't, anywhere the sun can find it. Ice on the sunlit moon would vanish almost instantly, boiling straight from solid to vapor and escaping into space. The only reason any water still exists up there is because of a quirk of the moon's geography. Because the moon barely tilts on its axis, some crater floors near the poles are angled so that sunlight never, ever reaches their deepest hollows. Not in summer, not at noon, not once. And those hollows are among the coldest places in the entire solar system, sitting somewhere around minus 240 degrees Celsius. That is roughly minus 400 Fahrenheit. Think of the coldest thing you have ever touched. Ice from a freezer, metal in deep winter that stings your bare skin. This is colder than anything your body has ever encountered, colder than almost anywhere else the sun's family of planets can offer. These are not craters. They are traps, cold traps. Any water molecule that ever wandered in, delivered by a comet, an asteroid, a chemical reaction in the soil, drifted down into that permanent dark, hit that impossible cold, froze solid, and never left. Some of these crater floors have stayed dark and stayed frozen for billions of years. When you look into one, you're looking at water that may have been locked in place since before complex life crawled across the Earth. A frozen archive, older than the oceans held any fish. And here is why that frozen archive changes everything. Because water on the moon is not just something to drink. Run an electric current through water, and it splits into the two gases it is made of, hydrogen and oxygen. That process, called electrolysis, is not exotic. It is a schoolroom experiment. But on the moon, that same simple reaction becomes the key to survival, because one of those gases, oxygen, is breathable air, and together, hydrogen and oxygen are also rocket fuel, the very same combination that has lifted spacecraft off the Earth for decades. So think about what a single crater of ice actually represents. Melt it, and you have drinking water and water for cooking. Pile it around a habitat, and its hydrogen-rich mass helps block the radiation pouring in from space. Split it, and you have breathable air on one side and rocket propellant on the other. One resource: water to drink, air to breathe, shielding to hide behind, and fuel to leave. On a world that offers nothing, water offers almost everything. And that last piece, the fuel, carries an implication that reaches far beyond the moon itself. Right now, every gram of fuel a deep space mission burns has to be dragged up out of Earth's deep gravity at enormous cost. But a spacecraft that could stop at the moon, refuel from lunar ice, and push onward would change the arithmetic of the entire solar system. The moon could become a filling station on the road to Mars and beyond. That is the dream, at least. That is the prize everyone is racing toward. But the prize is buried in the harshest ground a machine has ever been asked to work. because now we have to actually go and get it. And this is where the beautiful idea collides with brutal reality. To mine that ice, you have to send machines down into the permanent dark, into that minus 240-degree cold, and have them dig and keep digging reliably for years. And almost nothing we build behaves well at that temperature. Lubricants that keep moving parts sliding turn stiff and freeze. Seals meant to flex crack like old rubber. Electronics grow brittle. Batteries lose the ability to hold a charge, the same way your phone dies fast on a freezing winter day, except many times worse, in a cold no winter on Earth has ever come close to. And there is a deeper trap in the geography itself. The ice sits in the one place sunlight never reaches. But the machines need power, and the easiest power on the moon comes from the sun. So the energy to run the mine has to be generated somewhere in the light, then carried across distance down into the dark. You are trying to work in the coldest, blackest pit on the moon, powered by a sun you deliberately chose a spot to hide from. The very thing that preserved the ice for billions of years is the thing that makes it so punishing to reach. But even that is not the real argument. The real argument is about whether the ice is truly there in the amounts we are counting on. Here is the uncomfortable truth beneath all the excitement. We know there is water. What we do not agree on is how much, in what form, and whether we can actually get it out at scale. The optimistic reading says the poles hold vast, mineral reserves, enough to supply a permanent human presence for generations. But there is a more sobering possibility, and serious scientists hold it. The ice may not sit in convenient sheets you can scoop like snow. It may be scattered in thin patches or locked tightly into the rock and dust, mixed through the soil as scattered grains rather than pooled in veins, difficult and expensive and slow to pull free. We simply do not yet have the ground truth. Nearly everything we know comes from orbit and from a handful of impacts, not from a machine that has stood in a shadowed crater and actually dug. And the stakes of that uncertainty are enormous. A serious settlement, imagine a base of 100 people, could easily need hundreds of kilograms of water every single day, once you count drinking, food, hygiene, and the oxygen you crack out of it. That is not an occasional errand. That is continuous industrial-scale mining, running day and night, in the most hostile terrain any human machine has ever been sent to conquer. So the entire vision rests on a question no one has answered yet. Is the treasure real and reachable? Or is it a mirage frozen into the rock? We are about to find out. And the story of the machine meant to answer this question tells you everything about how uncertain this whole endeavor still is. NASA built a rover called Viper, a golf cart-sized robot designed to do one thing: drive into the polar region, drill into the surface, and finally map where the ice actually is, how much there is, and whether we can reach it. It was, quite literally, the scouts sent ahead to see if the treasure was real. And then, in the summer of 2024, with the rover essentially built and sitting finished in a clean room, NASA cancelled it. Cost overruns, delays. The agency had already spent around $450 million, and still they shelved it. The scout that was supposed to tell us whether the entire lunar water dream was viable was nearly taken apart for spare pieces. But the story did not end there. In September of 2025, NASA reversed course and revived the mission, this time handing the delivery to a private company, Blue Origin, to carry Viper to the South Pole on a commercial lander, with a target of reaching the surface in late 2027. Cancelled, then resurrected. The single most important scouting mission for lunar water almost did not happen at all. That is how fragile the ground beneath this dream really is. And here is what most people never realize. Even if the ice disappoints us, Even if it turns out to be patchy and stubborn and hard to reach, the moon may still hand us the one thing we need most. Because the air is not only locked in the ice, the air is locked in the rock. Consider the ordinary grey dust covering the entire moon, the regolith beneath every future boot print. By weight, that dust is somewhere between 40 and 45% oxygen, nearly half. Think about that for a moment. The most abundant element in the ground you would walk on, everywhere on the moon, is the very thing your lungs are desperate for. You would be standing on an ocean of oxygen the whole time. There is just one cruel catch. That oxygen is not free air. It is chemically bound, locked tight inside minerals as oxides, fused to metals like iron and silicon and aluminum. Picture rust. Rust is iron that has grabbed onto oxygen and won't let go. The moon's soil is, in a sense, a whole world of that kind of chemical grip. Oxygen held prisoner inside rock. To free it, you have to break those bonds, and breaking them means heat and electricity and something very close to smelting, the same brutal chemistry we have used for centuries to tear metal out of ore, now turned to tearing breathable air out of stone. Can we actually do it? We can, we have, and this is the reassuring part of the story. The European Space Agency built a working prototype that does exactly this. Researchers led by a chemist named Beth Lomax, working with ESA, took simulated lunar soil, heated it with a molten salt to around 950 degrees Celsius, and passed a current through it. The oxygen, pulled loose from the minerals, migrated out to be collected, and what remained behind was a mixture of usable metal. In their tests, they extracted almost all of the oxygen from the sample and were left with a metallic byproduct that a colony could use to build. NASA has been chasing the same goal along its own parallel paths, developing reactors to wring oxygen straight out of the regolith, air out of moon dust. It works. But, and this is the sentence that matters, it works on a bench, in a laboratory, on Earth. And a proof of concept in a lab is a very different thing from a machine that runs, unattended, at colony scale, year after year, on the surface of the moon. Between the two lies every hard problem there is: power, heat, maintenance, dust, breakdown, repair. Which brings us back to the deeper argument that sits under all of this, an argument no one has won. Every litre of water you can wring from a crater, every breath of oxygen you can pull from the rock, is one less thing you have to fly across the 239,000 miles, the roughly 385,000 kilometres of empty space between the moon and home. Every locally made thing chips away at that impossibly long supply line, and yet the reactors that make the air will still need spare parts, the mining machines will still break, and every one of those repairs for now still has to come from Earth. The question of whether making these things on the moon can ever truly beat shipping them from home remains genuinely unresolved. Making your own air and your own water is the first real test of whether a colony can stand on its own, the first true taste of independence from the home planet. But notice what every single one of these answers quietly depends on: the mining machines, the oxygen reactors, the heaters splitting rock at 900 degrees, the pumps, the lights in the permanent dark, the electrolysis pulling water apart. All of it needs one thing that everything else on the moon bows to: power, vast, constant, unfailing power. And the moon is about to reveal its cruelest trick of all, because it will offer us that power in abundance, and then every 2 weeks, without warning or mercy, switch it off and leave us in darkness for 14 days straight. 14 days of darkness. That is the trap waiting at the bottom of every plan to power a home on the moon. And to understand why it is so devastating, we have to first understand how spoiled we are down here. On Earth, energy is everywhere, layered and redundant, and in the ways that matter, almost free. Flip a switch and light appears. If the power fails, the sun still rises tomorrow. If a storm knocks out the grid, a generator hums to life, or a neighbor lends a cable, or the utility reroutes power from another line. We live inside a web of backups so deep we never see the bottom of it. You have never once in your whole life faced the possibility that all energy, every source, at once, might simply stop. On the moon, that possibility is not a nightmare. It is the schedule. Here is the mechanism, and it is deceptively simple. The moon turns, like the Earth turns, giving it a day and a night. But the moon turns slowly, so slowly that one full cycle from sunrise to sunrise takes about 29.5 Earth days. Think about what that means for the sky above a lunar base. The sun climbs, and it stays up, blazing, for roughly 14 Earth days without setting. Then it sinks below the horizon, and the darkness that follows lasts just as long, about 14 Earth days of unbroken night, 2 weeks of daylight, then 2 weeks of dark, every single month. And this is where the most obvious source of power on the moon reveals its fatal flaw. Sunlight is abundant up there, no clouds, no atmosphere to dim it. So solar panels seem like the natural answer. They work beautifully for 14 days, and then the sun goes down, and for the next 14 days those same panels generate almost nothing at all. A solar array on the moon is a machine that does its job perfectly, and then abandons you for 2 weeks, on a rhythm you cannot argue with and cannot change. So the obvious fix comes to mind immediately. Store the power. Fill batteries during the long day. Live off them through the long night. But run the numbers, and the idea collapses. Let's be honest about the scale of the problem, because this is where it becomes staggering. A serious base, habitats, life support, the oxygen reactors and mining machines we have already met, could easily demand hundreds of kilowatts of power continuously. To put that in human terms, a single kilowatt is roughly what a hairdryer pulls from the wall. Hundreds of kilowatts is a small town's worth of constant draw, and it cannot pause, because the moment life support stops, people begin to die. Now try to store 14 days of that in batteries. Not 14 minutes, not 14 hours. 14 days of unbroken town-size power, held in reserve, ready to release the instant the sun disappears. The mass of batteries needed to bridge that gap runs into the hundreds of tons. And remember the cruel arithmetic we keep returning to. Every kilogram launched from Earth costs thousands of dollars just to reach orbit, and far more to reach the lunar surface. Hundreds of tons of batteries at that price is not an engineering challenge. It is a financial impossibility. The math simply does not close. So the batteries can't save you. The panels can't save you. Which sends engineers searching for somewhere on the moon where the sun almost never sets. And remarkably, such places exist. Near the poles of the moon stand a handful of high points that astronomers, more than a century ago, gave an almost mythical name: the peaks of eternal light. The idea sounds like poetry, but the physics behind it is real. Because the moon barely tilts on its axis, the sun near its poles never climbs high and never fully sets. It just circles low around the horizon, skimming its edge all year long, and on certain elevated ridges, tall enough to stay above the surrounding shadows, that low sun almost always finds them. The rim of Shackleton Crater, sitting right at the South Pole, is the most famous of these. Its high points catch sunlight for something like 80 to 90% of each lunar cycle. A few spots on nearby ridges even more. Picture a mountaintop lighthouse standing above a valley drowning in shadow. The valley goes dark, the lighthouse keeps its light. That is what these peaks are, islands of near constant sun in an ocean of 2-week night. Stand a solar array up there, and you have almost solved the darkness. Almost. But here is the trap folding back on itself, in the most frustrating way imaginable. Because remember where the ice is. The water we came all this way to find sits at the bottom of those permanently shadowed craters, the exact places the sun never reaches, and the power to mine it, we now learn, comes from the peaks that the sun never leaves. The best sunlight and the best water sit miles apart, one on the sunlit heights, the other in the frozen dark below. To build a colony, you would have to generate your power in one place and carry it across rough and broken terrain to the place you actually need to use it, stringing lifeline cables between the light and the dark like a climber roping two separate ledges together across a chasm. It can be done, perhaps, but it is fragile, and it leaves the entire settlement leaning on a thin thread of sunlight and a long run of cable, which is why a growing number of engineers have started to say, forget the sun entirely. And here we reach one of the sharpest live debates in all of lunar planning, a genuine disagreement unfolding right now over how to keep the lights on. On one side, solar power, backed by whatever storage you can manage, clustered on those peaks of light. Clean, proven, simple, but chained to geography, and always haunted by that 2-week night. On the other side, nuclear fission, a reactor that splits atoms of uranium to make heat and heat to make electricity, and does it whether the sun is up or down, whether you sit on a sunlit peak or at the bottom of the darkest crater on the moon. A reactor does not care about the 14-day night. It ignores the day and night cycle completely. It is a private sun you bring with you and never have to wait for. And this argument is not theoretical anymore. It has moved, fast, into the real world. Here is what happened and how recent it is. In January of 2026, NASA and the United States Department of Energy signed a formal agreement, a memorandum of understanding, committing the two agencies to put a working nuclear reactor on the surface of the moon by 2030, and they set a specific target for its output, at least 100 kilowatts of electric power. Let me put that number in something you can feel. 100 kilowatts is roughly enough electricity to run 75 average American homes, all at once, on the surface of the moon. And here is the detail that reveals the urgency behind it. That figure is more than double the 40 kilowatt target the same program had been working toward just a few years earlier. In the span of a couple of years, the ambition doubled. But this is where the story gets honest and complicated, because not everyone agrees that bigger is wiser. Here is the doubt you might already be forming, and it turns out some of the very companies building these reactors share it. One of them, Lockheed Martin, has openly argued that a smaller reactor, in the range of 5 to 50 kilowatts, would comfortably cover the needs of the first habitats and rovers. Jumping straight to 100 kilowatts, in the words of one of their own directors, would increase program risk and provide more power than needed for what is actually planned in the near term. Think about what that means. One of the contractors hired to build the machine is gently raising a hand to say the headline number may be overkill. That is not a small tension. It sits at the center of a real and unresolved question. How much power does a base that does not yet exist actually need? And is the rush to a big number about survival or about something else entirely? We'll come back to that something else. First, the machine itself, because a reactor on the moon is far harder than a reactor on Earth. A nuclear reactor is a beautiful solution with a set of brutal complications, and every one of them gets worse in space. The first is radiation. The same fission that makes the power also throws out neutrons and gamma rays, invisible, penetrating, and dangerous to living tissue. So the reactor must be wrapped in heavy shielding, or buried, or set at a distance to keep colonists safe from the very thing keeping them alive. The power source becomes something you must also hide from. The second problem is stranger, and it comes straight from the vacuum we started this whole journey with. Every reactor makes waste heat, and on Earth that heat is easy to dump. You blow air across it, or run water through it, and the warmth carries away. But on the moon, with essentially no air, that escape route is gone. Heat cannot ride away on a breeze that does not exist. The only way to shed it is to radiate it directly into space, through large panels, slowly, the way a hot stone gives off warmth on a still night. Except this is the only cooling the machine will ever have. Build a reactor without enough of those radiator panels, and it cooks itself. And the third problem begins before the reactor ever leaves Earth. Its fuel is enriched uranium. For the American program, the Department of Energy plans to supply roughly 400 kilograms of it for testing and flight. That means launching nuclear material up through the one part of every mission that fails most often, the launch itself. Every rocket carries a real chance of exploding on ascent, and strapping a reactor's fuel to that risk demands a level of safety engineering and regulation unlike almost anything else we fly. Shielding, heat with nowhere to go, nuclear fuel on top of a rocket. None of it is impossible, all of it is hard. And now we come back to that something else, because the deepest force driving this race is not really about electricity at all. Consider two contradictory facts side by side. The reactor is being sold as the key to survival through the lunar night, and yet its own builders say the size being demanded is more than survival requires. So what is the extra power really for? The answer is written into the official directive itself, in language that is startlingly blunt. It warns that if China or Russia lands a nuclear reactor on the moon first, that first arriving nation could potentially declare a keep-out zone, a stretch of the most valuable ground on the moon, fenced off, that would significantly inhibit everyone who came after. Think about what that quietly means. The reactor is not only a power plant, it is a flag. Whoever powers the pole first may get to shape who is even allowed near its ice and its light. And this is not one nation racing alone. China and Russia announced their own joint plan for a lunar reactor, with a target somewhere between 2033 and 2035. 2 blocks, 2 reactors, both aimed at the same narrow band of sunlit ridges and frozen craters at the South Pole, the single most contested real estate off the surface of the Earth. The scramble to power the moon has quietly become a scramble to claim it. So step back and look at what power really is on the moon. Down here, if the lights go out, you light a candle and wait for morning. Up there, energy is not a convenience. It is the root that every other system grows from. The air you breathe is made by machines that need power. The water you drink is mined and melted by machines that need power. The heat that keeps your blood from freezing, the pumps, the lights, the sensors watching the pressure hull, all of it, every last thread of survival, traces back to a single source of electricity. And that is the quiet horror hiding inside the reactor solution. Build one reactor and stake the entire colony on it, and you have created a single point where everything can fail at once. A reactor breaks. There is no spare humming in the next valley, no grid to borrow from, no truck bringing a replacement by morning. When the power dies on the moon, it does not dim the lights, it stops the air. Energy, in the end, may be solvable. A reactor can be built, a peak can be wired, a battery can bridge a gap. But nothing on the moon is ever simple, and every solution we reach for turns out to be holding a knife by the blade. Because even if you win every one of these fights, even with power flowing and air being made and water running clear, the moon has been quietly working on you the entire time. Not on your machines, on you, on your body, on your skin, and your blood, and your lungs. There is something in the very ground you would walk on, and something pouring down from the sky above it that no reactor, no wall, and no amount of power can switch off. And it has already begun to do its work. It began, as it always does, with something small enough to ignore. Dust. Not the soft, harmless dust that gathers on a bookshelf, the kind you wipe away with a fingertip and forget. The dust on the moon is something else, something that Apollo astronauts learned to fear and that no colony has yet found a way to defeat. To understand why a fistful of grey powder could threaten an entire settlement, we have to understand where it came from, because its history is written into every jagged edge. Here on Earth, dust is gentle because Earth is gentle to it. Wind tumbles each grain against its neighbours. Water rolls them smooth. Over time, every particle gets worn round, like a pebble in a riverbed, softened by weather and age. The Moon has had none of that. For roughly 4 billion years, no wind has blown across it, no rain has fallen, no river has run. And in all that time, something else has been shaping the dust instead. Meteorite impacts, an endless silent bombardment, striking the surface and shattering the rock over and over across an unimaginable stretch of time. The result is a dust made not of smooth grains but of tiny broken splinters, sharp, angular glass-like shards, frozen mid-fracture and never once worn down, fine like powder but sharp like broken glass. Run your bare hand through it and it would not feel soft. It would cut. But sharpness is only the first of its weapons. And here is where the story turns strange. The Moon has no protective air, so the raw sunlight striking its surface carries a component we are shielded from down here. Ultraviolet light, strong enough to knock tiny electric charges loose from the dust itself, and a charged grain does not behave like ordinary dirt. It does not simply lie there. It repels its neighbours, lifts off the ground and drifts, floating sideways, hovering above the surface, clinging to anything it touches. Think of a balloon rubbed against your hair and how strands rise up to follow it across the room, standing on end, reaching. Now imagine an entire landscape of dust behaving that way. It doesn't settle onto equipment, it comes for it. That is the part most people never grasp. Lunar dust is not passive, it migrates. We are not guessing at this. We watched it happen. When Apollo astronauts walked the surface in the 1960s and 70s, the dust invaded everything. It ground into the joints of their spacesuits, abrading the fabric visibly after only a few hours of work, wearing down gear that was meant to last in a single afternoon. It coated their visors, it jammed their equipment, and when they climbed back inside and removed their helmets, they breathed it in. Harrison Schmitt, a trained geologist and one of the last men to walk on the Moon, got a lungful during the Apollo 17 mission. Within hours, his eyes watered, his throat grew sore, his sinuses swelled until you could hear it in his voice. He called it lunar hay fever. And here is the detail that should stop you. It wasn't just him. In some form, all 12 of the men who ever stood on the Moon reacted to the dust. One flight surgeon, simply handling their dust-covered suits back on Earth, reacted so badly he had to stop. Now stretch that from a 3-day visit to a permanent colony. The same dust that abraded a suit in an afternoon would be gnawing at machines meant to run for years. It jams airlocks, chews through seals and gaskets and hinges, scratches visor coatings blind. Left on solar panels, a thin film of it can cut their power output by an estimated 20 to 40%. Imagine a third of your electricity quietly vanishing under a layer of grime you can never fully wipe away. On a world where power is the root of survival, the dust is slowly, patiently strangling the very machines keeping you alive. But the sharpest question isn't about the machines, it's about the lungs. And this is where the science splits, a real, unresolved disagreement about how dangerous this dust actually is to the human body. For years, the alarming evidence piled up. NASA-funded studies exposed rat lungs and human cells to lunar dust and its simulants, and the results were troubling. Inflammation, oxidative stress, even damage to DNA, the molecular blueprint inside every cell. One study found lunar dust caused cell death and genetic damage in lung tissue. The picture that emerged was of a material that might, over years of exposure, do to a colonist's lungs something like what a lifetime in a coal mine does to a miner. But then, in 2025, a study from the University of Technology, Sydney, complicated that fear. Researchers took the most accurate modern dust simulants and exposed human lung cells to them, then compared the damage to something ordinary, the fine particle pollution off a busy Sydney street. And the finding was genuinely surprising. The lunar dust irritated the cells, scraping at them with its rough edges, but it caused less severe inflammation, less toxic damage than the everyday city air that millions of people breathe without a second thought. A physical irritant, the lead researcher stressed, is not the same thing as a poison. So which is it? A silent killer or an overblown fear? Here is the honest answer, and it matters. Both findings may be true at once, because they may not be studying the same thing. The reassuring study used simulants, manufactured stand-ins for real moon dust, and freshly ground, real lunar regolith may be far more dangerous than any earthly copy. Its broken surfaces chemically raw, reactive, hungry to react with living tissue in ways a lab-made powder cannot capture. On the moon, the dust is freshly shattered. In the lab, it never is. We simply do not yet know which moon we would be breathing, and the uncertainty itself becomes a design problem because you cannot build a colony around a maybe. To be safe, every habitat would need filtration that traps particles just 1 or 2 microns across, specks so small that dozens of them would fit across the width of a single human hair. And that filtration cannot take breaks. Not overnight, not for maintenance, not for a single hour. It would have to run continuously forever, scrubbing invisible glass from the air the colonists breathe, because the moment it fails, the dust they carried inside on their suits begins lifting back into the air with every footstep. Engineers have a promising idea: electrodynamic dust shields, surfaces that use pulsing electric fields to push charged dust off of them, almost like a windshield wiper made of invisible force instead of rubber. It is clever. It may work, but it remains largely unproven at the scale a real colony would demand. And even a perfect dust defense would leave the deadlier enemy untouched, because while the dust attacks from the ground, something far more dangerous is falling from the sky. Here is a fact so fundamental we almost never think about it. Right now, as you sit reading this, you are being protected by 2 invisible shields you did not ask for and have never once seen. The first is Earth's magnetic field, a vast, unseen force generated deep in our planet's molten core, wrapping the entire world in a cocoon that deflects the charged particles streaming at us from space. The second is our thick atmosphere, that same ocean of air we met at the very beginning, which absorbs what the magnetic field lets through. Between them, they intercept the overwhelming majority of the cosmic radiation aimed at your body every second of your life, and you never feel a thing. The moon has neither. No magnetic cocoon, no blanket of air, nothing. So whatever comes screaming in from space does not get deflected, and it does not get absorbed. It arrives at the surface directly, and it strikes whatever is standing there, unfiltered, full strength. And now, for the first time, we know exactly how much. In 2019, China's Chang'e 4 lander touched down on the far side of the moon, carrying an instrument built to answer a question the Apollo missions never properly measured: how much radiation actually reaches the surface. The answer, published soon after, was sobering: about 1,369 microsieverts per day. That number means nothing until you feel it, so here it is. Standing on the surface of the moon, you would absorb roughly 200 times the radiation dose you receive right now on the surface of the Earth. 200 times, not twice as much. 200 times over, every hour, every day, soaking into your body with nothing between you and the source. And most of that dose, around 3/4 of it, comes from something you can never turn away from: galactic cosmic rays. These are atomic particles hurled across the galaxy by ancient, distant supernova, the death explosions of stars, traveling at nearly the speed of light, so energetic they punch straight through metal, through walls, through flesh, leaving microscopic damage in their wake. They come from every direction, all the time. There is no downwind, there is no hiding on the far side of the habitat. They simply rain through everything, and through you, without pause. That is the background hum of danger. But the moon has something worse than a hum. It has storms. Every so often the sun does something violent. It flares, hurling out a sudden massive burst of high-energy particles in what scientists call a solar particle event. And when one erupts toward the moon, the warning time can be brutally short. Tens of minutes, sometimes less, barely enough time to run. Here is why that should chill you. A single major solar storm, striking an unprotected human on the lunar surface, could deliver a dose high enough to cause acute radiation sickness, or to kill outright. And we know these monsters are real because one has already happened. In 1859, a solar storm so powerful it set telegraph lines sparking swept over the Earth, an event we now call the Carrington event, after the astronomer who watched it unfold. Down here, our atmosphere absorbed the blow, and we survived it with little more than dazzling auroras and burnt wires. But a storm like that, catching an astronaut exposed on the surface of the moon, with no air and no magnetic field to soften it, would very likely have been fatal. Think about what that means for daily life up there. Every colonist would live with a countdown they cannot see, knowing that on any given day the sun might give them minutes to reach cover, or the difference between living and dying could come down to how fast they can run to a shelter, which is why that shelter is not optional. A radiation storm shelter, a room shielded thickly enough to stop a killing dose, would be as fundamental to a lunar home as the pressure hull that holds the air itself. Not an amenity, a lifeboat. But even building that shelter hides a trap, and it is one of the most counterintuitive dangers in all of space travel. You would think the obvious answer is to wrap the shelter in something heavy and solid. Thick metal, dense armor, the instinct of every fortress builder in history. Except, with cosmic radiation, that instinct can betray you. When those high-energy particles slam into heavy atoms like the ones in metal shielding, they don't simply stop. They shatter the atoms, spraying out a shower of new, smaller particles, secondary radiation, that can leave you exposed to a worse dose than if you'd used no shielding at all. The wall meant to protect you becomes a source of the very thing it was blocking. The materials that actually stop this radiation best are the light ones, rich in hydrogen, the lightest element of all. Water, plastics like polyethylene, the same water you drink and the same water you'd mine from those frozen craters, turns out to be one of the finest radiation shields there is, which is why one of the smartest defenses is to surround your shelter, not with steel, but with tanks of your own water supply. Stack it all together, the abrasive, migrating dust, the invisible glass in every breath, the constant cosmic rain, the sudden lethal storms, the shield that can backfire, and the engineers keep arriving at the same conclusion, the same one we've circled toward more than once already. Stop trying to survive on the surface, go under it, bury a habitat deep enough beneath the regolith, and a strange kind of peace settles over almost every problem at once. The meters of rock and dust overhead swallow the cosmic rays. They stop the solar storms. They hold back the killing chill of the long night and the searing heat of the long day. The dust that migrates and cuts and clogs stays outside, above you. Underground, the moon finally goes quiet, and in 2024, that idea stopped being a hopeful sketch and became something real. Analyzing radar data from a lunar orbiter, An international team confirmed for the first time an actual cave beneath the moon's surface, an accessible tunnel, tens of meters long, hidden below a pit in the Sea of Tranquility, not far from where Apollo 11 first touched down. A ready-made shelter, carved by ancient lava, waiting in the dark. Nature, it seems, may have dug the first storm cellar for us. But sit with what that actually means for the people who would live there. To survive the moon, you would have to give up the surface of the moon. No open sky, no sunlight on your face, no horizon to walk toward. A life spent almost entirely indoors, sealed away, buried, glimpsing the outside only through a screen or through the narrow visor of a suit during dangerous rationed excursions. We dreamed of standing on another world. The reality would be spent hiding beneath it, and that raises the most unsettling question of all, one that has been waiting quietly beneath every hazard we've named so far. We have talked about protecting the body from the vacuum, from the cold, from the dust, from the radiation, as though the body itself would otherwise be fine, as though, once you seal it away safely underground, a human being would simply carry on as they do here. But they would not, because the moon has one more way to change a person, slower than any storm, quieter than any dust, and impossible to hide from, even in the deepest cave. It works on the body from the inside, and it begins the moment you arrive, in a force so gentle you would barely notice it was different at all. You would barely feel it at first. That is the strangest part. Step onto the moon and the thing quietly rewriting your body would announce itself as something almost pleasant, a lightness. You'd weigh a sixth of what you weigh here. A person who tips the scale at 180 pounds on Earth would feel like they weigh just 30 on the moon. You could bound across the surface like the Apollo astronauts did, half floating, grinning inside your helmet. It would feel like freedom. And that lightness is the trap, because the human body was not designed in the abstract. It was built, cell by cell, across hundreds of millions of years, by one specific force pulling downward at one specific strength, the gravity of this planet. Take that force away, or even weaken it, and the body does not simply cope. It begins to remodel itself for a world it was never meant to live in, slowly, silently, from the inside. And to understand what the moon would do, we first have to look at what we already know happens when gravity disappears entirely. Here is where the science is not speculation. It is documented in the bodies of hundreds of astronauts across decades aboard orbiting stations. And it is unsettling. Take away gravity and your bones start to vanish. On Earth, your skeleton is under constant gentle load. Every step, every time you stand, your bones feel your weight and know they are needed. Remove that signal, and the body, ever efficient, begins dissolving bone it thinks it no longer requires. In orbit, astronauts lose roughly 1 to 2% of their bone density every single month in the weight-bearing bones, the spine, the hips, the legs. Let that number breathe for a moment. On Earth, a postmenopausal woman at real risk of osteoporosis loses bone at about 1 to 2% per year. An astronaut loses that same amount in a single month, roughly 12 times faster. 6 months in orbit can cost as much bone as an entire year of aging does to someone already losing it dangerously fast. Their skeleton thins toward fragility, 1 month at a time, and the bones are only the beginning. The muscles, no longer fighting gravity, waste away, atrophying the way a limb withers inside a cast, except it happens to nearly every muscle at once. The heart, which on Earth works constantly to pump blood upward against your weight, suddenly has an easier job, and it too begins to weaken and deform, like any muscle that stops being asked to work hard. But the eeriest change happens in the eyes. On Earth, gravity is always gently pulling the fluids in your body downward toward your feet. Take gravity away, and those fluids, blood and the clear fluid around your brain, drift upward instead, pooling in the head and pressing outward from behind. And that rising pressure pushes on the back of the eyeball itself, slowly flattening its perfect curve, swelling the optic nerve, folding the retina. Astronauts return with their vision measurably changed, many of them newly farsighted, their eyes reshaped by the fluid that no longer knew which way was down. Scientists gave this a name: spaceflight-associated neuroocular syndrome. NASA now rates it among the most serious medical risks of long journeys in space. The body, adrift, begins to reshape the very windows through which it sees. So that is zero gravity, a body slowly unmaking itself. But here is the question that should be keeping the planners awake at night. The moon is not zero gravity, and this is where our confidence collapses into a void. Everything we just described, the vanishing bone, the wasting muscle, the flattening eye, comes from weightlessness, from floating in orbit at essentially zero gravity. The moon is different. It pulls at 1/6 of Earth's strength. Not nothing, but not nearly full. Somewhere in between, a strange middle ground that our bodies have never been tested in. And here is the fact that should stop every colony dreamer cold. We have almost no idea what 1/6 gravity does to a human being over time. None, because no human has ever spent more than about 3 days in it. Add up every moment that every Apollo astronaut ever spent walking on the lunar surface across all 6 landings in history, and the total comes to under 80 hours, less time combined than a single work week of a single office job. That is the entire human experience of living in lunar gravity. Barely 3 days, spread across a dozen men, half a century ago. We are, in the most literal sense, flying blind. And when we go looking for answers in the lab, the answers we find are not reassuring. Here is what scientists did, because they could not yet do it with people. Aboard the International Space Station, Japanese researchers built something remarkable: a small centrifuge that could spin cages of mice fast enough to simulate exactly 1/6 gravity, the pull of the moon, while floating in orbit. For the first time, living animals could be raised in lunar gravity and studied, and the results refused to give a simple answer. The good news came first. That lunar strength pull was enough to prevent the worst of the muscle wasting. The mice's muscles did not collapse the way they do in true weightlessness. 1/6 gravity, it seemed, was enough to keep some things alive and working. But then came the unsettling part. Even though the muscles kept their size, something inside them still changed. The very type of muscle fiber began shifting, converting toward the kind you'd find in a body doing far less work. And the bones were only partially protected. The lunar gravity slowed their loss, but it did not stop it. Different tissues, it turned out, had different breaking points. Muscle needed one amount of gravity to stay healthy. Bone needed more. Some systems seemed to want the full pull of Earth, and nothing less would fully satisfy them. Think about what that means. The body is not one machine with one gravity switch. It is a collection of systems, each with its own hidden threshold, and 1/6 gravity may sit above the line for some and below the line for others. Enough to save the muscle, not enough to save the bone. A body caught halfway between health and decline, permanently. And that is with adult mice, studied for weeks. Now stretch the question across a human lifetime, and then across the birth of a child. Here is the possibility that turns this from a medical problem into something far stranger and more permanent. Consider a child born on the moon, not visiting, born there, conceived, grown, and delivered under that 1/6 pull and raised in it from the first breath. That child's body would not be adapting to lunar gravity. the way an astronaut's does. It would be built for it from scratch. Their bones would grow calibrated to a weaker pull. Their heart would develop to move blood through a body that has never weighed what yours weighs. Their muscles would form around a world where everything is light, and that child might grow up perfectly healthy for the moon. But here is the quiet horror inside that. A body optimized from birth for 1/6 gravity might never be able to withstand the full crushing weight of Earth. Their underbuilt bones and underpowered heart dropped suddenly into a gravity 6 times stronger than any they had ever known, might simply fail, unable to stand, unable to pump blood upward, collapsing under a weight the rest of us carry without a thought, which leads to a conclusion that sounds like science fiction, but follows directly from the biology. A generation born on the moon could become the first humans in history physically unable to visit the planet their species came from. Earth, every ocean, every forest, every face of every ancestor, would become a place they could see hanging in their black sky and never once set foot upon, homesick for a home that would break them. And we do not even know if that child could be safely born at all. Because here is a gap in our knowledge so complete, it's almost vertigo-inducing. We have essentially no idea how human reproduction works in partial gravity, whether a pregnancy can proceed normally, whether an embryo, dividing and folding itself into a body, can build correctly without Earth's pull to orient the process, whether the delicate architecture of a developing brain and spine assembles the way it should when down is only a 1/6 as strong. No one knows. It has never been tested, not in humans. And layered on top of that unknown is the danger we already met: radiation. Remember that constant cosmic rain, 200 times what we feel on Earth, that no habitat fully stops. Now aim it at the most vulnerable cells that exist, the rapidly dividing cells of an embryo, of a developing child. Radiation damages DNA most easily when cells are dividing fastest, which is exactly what a growing baby's cells do. The risk to a pregnancy and to early development is real, and it is almost entirely uncharacterized. We would be gambling with the beginning of a human life in conditions we have never studied and cannot ethically rehearse. But set aside the far future of moon-born children. Return to the colonists themselves, alive and adult, and consider a simpler, more immediate terror. What happens when one of them gets sick? On Earth, medicine works because it escalates. Feel a pain? You see a local doctor. The doctor sends you to a hospital. The hospital, if needed, sends you to a specialist centre with machines and surgeons that a small clinic could never hold. Each level hands you upward to a bigger, more capable one. You have lived your whole life inside this invisible safety net and never once had to think about how many hands are ready to catch you. On the moon, there is no escalation. There is no next level up. Care is whatever happened to arrive on the last supply ship. The equipment in the room, the training in the crew, and nothing more. There is no bigger hospital to send you to. The hospital is the room you're standing in, and it is the only one for 250,000 miles. And bodies break unpredictably. A burst appendix, a heart stopping, a stroke, an accident that shatters a bone. These strike ordinary people on Earth every single day, and here they're survivable because help is close. On the moon, an appendix that would be a routine surgery in any Earth town could become a death sentence, not because the problem is harder, but because the help isn't there. And even the help that is there would be working half blind. Think about what surgery even means in 1/6 gravity. On Earth, a surgeon relies on gravity constantly, without noticing. Blood pools downward and can be suctioned away. Fluids settle. Everything behaves predictably. In lunar gravity, blood and fluids would behave in ways no surgeon has ever fully trained for. Drifting, beading, refusing to settle where they should. The operating field itself would misbehave. Even putting a patient safely to sleep becomes a question mark. The way anesthesia moves through the body, the way the lungs and circulation respond under a drug in reduced gravity, much of it remains uncharacterized. We would be doing some of the most delicate work medicine knows, in physical conditions we have barely begun to understand. So every colonist would need to be far more than their job title. Each would need deep medical and emergency training, ready to become a surgeon's hands in a crisis. Experts back on Earth could watch and advise over a video link. The moon is close enough that a conversation can happen almost in real time, but advice is all they could offer. A doctor on Earth cannot reach through a screen and clamp a bleeding artery. When the moment comes, the people in that buried room are utterly, terrifyingly alone with it, and even the medicines meant to save them are quietly working against the clock. Drugs are not permanent. They degrade. Every pill in your cabinet carries an expiration date for exactly this reason. But in space, that decay may run faster. Studies of medications stored aboard the space station found that some degraded more quickly than their Earthbound twins, a number of drugs slipping below their rated potency before their expiration dates even arrived, with radiation suspected as one of the culprits. Some medicines need refrigeration that must never fail. Others simply lose their strength on a schedule no one can stop. And here is the hardest limit of all. A medication that is not on the supply manifest does not exist. On Earth, if a pharmacy lacks a drug, another one across town has it, or it's flown in overnight. On the moon, if the specific medicine a dying colonist needs was not packed and was not made there, then for all practical purposes it is not real. It cannot be summoned. The nearest dose is 250,000 miles away, months from arriving. Which points to a staggering conclusion. To be truly safe, a colony might not just need a pharmacy. It might need to manufacture its own drugs, to become its own pharmaceutical industry, synthesizing medicine from raw chemistry on the moon, because the alternative is watching people die of treatable things. So here is where the journey has quietly brought us. We began by armoring the colonist against the outside, the vacuum, the cold, the dust, the radiation. We buried them safely underground. And now we find that even sealed in the safest cave on the moon, with the air made and the water flowing and the power humming, the danger was never only outside. It was in the gravity that greets them at the door, in the bone that thins and the eye that flattens, in the child who could never come home, in the burst appendix with no hospital, the surgery in a world without down, the medicine that isn't on the shelf. The moon does not need to breach the walls to harm the people inside. It works on them through the very floor they stand on and the very cells they're made of. And yet, every problem we have named so far, brutal as it is a problem of keeping a single body alive. Air for the lungs, water for the blood, gravity for the bones, medicine for the sickness. But a colony is not one body. It is a crowd of them, sealed together in a small buried space for years, with no way out. And human beings need more than air and water and working bones to survive that. They need to eat, and they need something harder to measure and just as easy to lose. They need to not come apart on the inside from one another, because a habitat with a flawless hull and endless power and perfect medicine can still be destroyed, not by anything the moon does to it, but by what the people inside it do to each other and to their own minds in the long, sealed dark. And the first thread that could unravel it all is the most basic one of all: food. Food. It sounds almost quaint, next to vacuum and radiation and the slow theft of your own bones. A garden, something green, growing behind glass, under a black sky. And it is one of the most seductive images in every vision of a moon colony. Rows of crops glowing under lights, a self-made harvest, humans coaxing life out of a dead world. But that image hides the single most fragile thread in the entire enterprise, because a colony that cannot feed itself is not a colony. It is a countdown, and the first thing that betrays the dream is the ground itself. Here is a distinction almost no one makes until it matters enormously. The moon has no soil. That sounds wrong, because the moon is covered in that grey dust and rubble we keep returning to. But dust is not soil, not in the way a farmer means the word. Real soil, the kind under a garden on Earth, is not just crushed rock. It is alive. Reach down and take a handful of it, and you are holding a teeming, invisible city. Billions of bacteria, threads of fungi, tiny organisms, and the slow chemistry of decayed life, all woven together across thousands of years. That living web is what feeds a plant. Soil is not a thing. It is a process, a partnership between rock and life that Earth spent ages building. The moon has none of that. What covers the moon is regolith, pulverized rock, sterile, dead, never once touched by biology. And it is not merely empty. In places, it is openly hostile to anything trying to grow. It carries toxic traces of metals, and it lacks the very nutrients a plant cannot live without. No nitrogen, no usable phosphorus, none of the chemistry a seed expects to find when it sends out its first root. So the obvious question is, the one scientists finally, recently, decided to actually test. Could anything grow in it at all? In 2022, at the University of Florida, two scientists named Annalisa Paul and Robert Furl did something no one had ever done. For over a decade, they had petitioned NASA for a piece of the most precious dirt in existence, real lunar regolith, brought back by the Apollo astronauts half a century earlier. They were finally granted a vanishingly small amount, about 12 grams total, just a few teaspoons, split into thimble-sized pots holding barely a gram each. Into that ancient moon dust, they planted seeds of a small, fast-growing plant that scientists know better than almost any other. And they waited, not really believing anything would happen. The seeds sprouted. "We were amazed," Paul said. "We did not predict that." Against every expectation, life had taken root in soil from another world. For a moment it looked like the dream was real, but then they looked closer. The plants had grown, but they had grown wrong. Stunted, slow, smaller and sicker than their cousins planted in ordinary Earth material. And when the scientists ground them up and read the activity of their genes, the internal switches a plant flips to survive, they found something quietly disturbing. The plants had switched on the exact genes a plant uses when it is drowning in salt, or poisoned by heavy metals, or under chemical attack. In other words, the plants were not thriving, they were suffering. They had sprouted into a hostile world and were frantically firing every emergency system they had just to stay alive. They looked, in the researchers' own framing, like plants fighting for their lives. And there was one more detail, small and strange and telling. When the scientists tried to water the lunar soil, it fought back. The regolith repelled the water, made it bead up on the surface and refused to soak in, behaving the way a freshly waxed car sheds rain. The dust did not want to be a garden. Every instinct of the moon resisted the intrusion of life, so growing food directly in the lunar ground, the way we have farmed for 10,000 years. That door is, for now, effectively closed, which forces the colony to abandon soil entirely. The answer is to grow food with no soil at all. Hydroponics, feeding plant roots directly with water laced with exactly the right nutrients. Aeroponics, misting bare roots with a nutrient fog, the plant suspended in air. No dirt, just roots, water, chemistry, and light. And light, for a long time, was the killer problem. Plants need enormous amounts of it, and older artificial lighting devoured electricity. and we have already seen how brutally scarce every watt of power is on the moon. But here, at least, one piece of good fortune arrives. Modern LED lighting, the same efficient technology now lighting your home, has finally become efficient enough to make indoor growing energetically thinkable. Tuned to the exact colors plants use most, LEDs can feed a crop while sipping power where old bulbs would have gulped it, so we can grow food without soil under lights. The dream survives until you do the arithmetic of scale. Here is where hope collides with mathematics. Feeding one single person a full, balanced diet from crops takes a genuinely large growing area. Estimates commonly land somewhere around 80 to 100 square meters of continuous cultivation per person. Picture that. To feed one human being, you need a garden roughly the size of a modest apartment, or about a third of a tennis court, planted wall to wall, producing without pause. Now scale it up. A colony of 100 people would need thousands of square meters of crops, not a greenhouse, an indoor farm the size of several football fields, and every square meter of it would have to be lit by those LEDs, heated against the cold, and, the detail that makes it staggering, pressurized. Every one of those fields would be its own sealed pressure vessel, holding air against the vacuum, drawing power every second for as long as the colony wished to eat. And here is the implication that turns a farm into a knife's edge. On Earth, if a harvest fails, drought, blight, frost, you buy food from the next region, the next country. There is always somewhere else. On the moon, there is no next region. There are no imports arriving on demand, and no supermarket stockpile to fall back on. The farm the colonists built is the only food that exists for 250,000 miles. A serious crop failure, a disease sweeping the sealed rows, a lighting system going dark, a pressure loss in the growing modules would not mean tightening belts. It would mean starvation with no one to call. The garden is not a comfort. It is a lifeline stretched thin, and to survive at all, that farm cannot simply consume and discard. It has to become part of something far more ambitious and far more fragile, a closed loop. On Earth, we take resources and throw the waste away, and the planet quietly absorbs and recycles it for us, invisibly, for free. A colony cannot afford to throw anything away. Every drop of water a plant breathes out into the air must be captured back and reused. Human waste, every bit of it, must be processed and turned into fertilizer to feed the next crop. The water, the nutrients, the very air, all of it must cycle around and around in a sealed circle, because every input that isn't recycled becomes yet another thing that must be flown across the void, another vulnerable thread in the supply line. The colony must become its own miniature Earth, running all the cycles our whole planet runs, inside a buried box. And here is the sobering truth. We have tried to build a closed living world before, and it has never truly worked. In 1991, in the Arizona desert, 8 people sealed themselves inside an enormous glass structure called Biosphere 2, a 3-acre miniature Earth, complete with a tiny farm, a rainforest, even a small ocean, all closed off from the outside world. The goal was breathtaking. Prove that humans could build a self-sustaining slice of Earth, a rehearsal for living on other worlds. They meant to stay 2 years, and almost immediately, something began to go wrong that no one had predicted. The oxygen started disappearing. Slowly, steadily, the air inside grew thinner. It had begun at the normal 21% oxygen we all breathe. Over about 16 months it fell to around 14%. To feel what that means, the crew were suddenly breathing the air of a mountain peak nearly 3 miles high without ever leaving the desert floor. They grew exhausted. They gasped, climbing stairs. One member became so oxygen-starved he could no longer add up a simple column of numbers. Eventually, to protect them, Oxygen had to be pumped in from outside. The sealed world had failed to keep its own crew breathing. And here is the part that should haunt every colony planner. The cause was almost invisible. Microbes in the rich farm soil were consuming oxygen faster than the plants could make it, and the concrete of the structure itself was quietly absorbing carbon dioxide, breaking the chemistry the whole system depended on. The failure did not come from some dramatic disaster. It came from a surface nobody had even thought to count as part of the ecosystem. That is the terror of a closed loop. It contains everything inside it, including the things you forgot were there. Biosphere 2 was not alone in revealing this fragility. Other long isolation experiments, crews sealed away to simulate journeys to Mars or living in remote habitats, keep teaching the same lesson. Sealing a functioning world inside a wall is far, far harder than it looks. No closed ecosystem has ever proven reliable at the scale a real colony would need. Not once. But a slow leak of oxygen is not the fastest way a sealed world can turn on its inhabitants. There is a much quicker one. Consider fire. On Earth, a fire is dangerous, but a room has doors, windows, open air. Smoke rises and escapes, and you flee into a world full of clean air. In a sealed habitat, none of that exists. A fire has nowhere to vent, the smoke has nowhere to go, and the toxic gases it produces don't disperse into the sky. They fill the single, shared atmosphere that everyone inside is breathing, the only air there is. And the deadliest of those gases gives no warning. Carbon monoxide is invisible and odorless. You cannot see it, cannot smell it, cannot taste it. It slips into your blood and quietly takes the place of oxygen, and by the time you feel it, you may already be too impaired to save yourself. It incapacitates before it announces itself. This is not hypothetical. We have watched it nearly happen. In 1997, aboard the Russian space station Mir, a device meant to generate oxygen suddenly ignited, spraying a jet of flame and molten metal across the module. The crew scrambled for masks, some of which failed, and found the fire extinguishers strapped down so tightly they could barely tear them free. One of the two escape craft was blocked by the flames themselves. The fire burned for about 14 minutes, 14 minutes that must have felt like hours, before it finally died, and thick smoke hung in the station's air for long after. They survived, but it was close, and it happened in a tin can far smaller than any colony, where every second and every breath was counted. So a lunar habitat would have to be built around the constant fear of fire, fireproof materials wherever possible, fine mist suppression systems, the ability to seal off and isolate compartments so a fire in one cannot doom them all. The dream of a cozy home underground runs headlong into the reality that in a sealed box, a single flame is a threat to everyone at once. And yet, even a perfect defense against leaks and failures and fire would leave one last vulnerability, the most unpredictable one of all, the people themselves. Because a colony is not only a machine to be maintained, it is a small group of human beings sealed in a confined space, buried under rock, unable to step outside into open air, cut off from everyone they have ever known for years. And we know with hard evidence what that does to people. Our best window into it sits at the bottom of the world. In Antarctica, a research station named Concordia keeps small crews sealed in through the long polar winter. Months of darkness, cold, and total isolation, unable to leave, the closest thing on Earth to living on another world. And researchers studying those crews found something remarkably consistent, a pattern they call the third quarter effect. It works like this. The crews cope reasonably well at first, buoyed by novelty. They cope near the end, lifted by the coming release. But in the third quarter of the mission, past the halfway point, with the end still far off, morale and mental sharpness measurably sag. People withdraw, coping strategies falter, a kind of psychological hibernation sets in. And here is what makes it chilling. That dip happens to carefully screened, psychologically robust volunteers, people chosen for their stability, who signed up willingly and who know the exact date they get to go home. They have an escape hatch waiting on the calendar, and still the isolation reaches into them and pulls them down. Now take away the departure date. A lunar colonist has no fixed day of release, no easy evacuation waiting if things get hard, no next ship for months, and no simple ride home even then. The one comfort that helps the Concordia crews endure, knowing it ends, may not exist at all, which means a colony needs far more than air and food and power. It needs real governance, ways to resolve conflict before it festers, and something as simple and as vital as genuine private space, a door a person can close, a place to be alone, on a world where there is nowhere to escape to. So look at what we have arrived at quietly at the end of all this engineering. We have built a hull that holds the vacuum out. We have made air and mined water and grown food and generated power and shielded against radiation and buried ourselves safe beneath the surface. We have solved, at least on paper, every threat the moon throws from the outside. And a flawless pressure hull can still fail from the inside. Not from a leak, not from a strike, but from a fire in the shared air, or a slow poisoning no one smelled, or a crop that failed with no harvest to replace it, or from something quieter and harder to engineer against. People coming apart in the dark, from the isolation, and from one another. The wall that holds back the void is only as strong as the fragile, breathing, fallible human system living inside it. But suppose even that holds. Suppose the people stay sane, and the loop stays closed, and the fire never comes. There is still a force working against the colony that never sleeps, never negotiates, and never stops. And it is not trying to kill the people at all. It is trying to kill the machines. Every wall, every seal, every reactor, every suit, every rover the colony depends on is, from the moment it arrives, beginning to break down, faster than anything ever breaks down on Earth. And on the moon, when a thing breaks, there is no one coming to fix it but you. The colony's true enemy, it turns out, may not be the moon at all. It may be time. Time. Not the ticking of a clock, but the slow, patient force that wears every made thing back down toward dust. On Earth, we barely notice it. A hinge that squeaks after a decade, a roof that needs replacing after 30 years. On the moon, that same force moves faster, and it never once stops working, because everything a colony depends on is a machine, and on the moon, machines die younger than they ever would on Earth. That sounds like a small problem next to vacuum and radiation and starvation. It is not. It may be the quietest killer of them all, because it doesn't strike once. It grinds continuously at every single object standing between the colonists and the void, and it demands, in return, an unending labour that never finishes and never lets up. Let me be precise about why the moon ages machines so cruelly. 3 forces work on every device up there, all at once, all the time. The first is radiation, the same cosmic rays we watched pour down on human bodies. But they don't only harm flesh. Each of those high-energy particles, when it strikes a microchip, can flip a tiny switch, corrupt a calculation, or leave a microscopic scar in the silicon. One strike is nothing, but they never stop coming, and the damage accumulates like a stone wall pelted by an endless, invisible hail, each impact meaningless, the sum of them ruinous. Engineers can harden electronics against this, shielding and reinforcing them. But hardening only slows the decay. Every component still has a hard limit, a point past which the accumulated damage wins. The second force we have already felt, the savage temperature swing, that 300-degree lurch between the 2-week day and the 2-week night. Every material expands in heat and contracts in cold, and different materials do it by different amounts. So every seal, every joint, every weld is stretched and squeezed with each long cycle. And here is the quiet trap in it. Many of these seals are rated for only a finite number of cycles before they fail, a number the manufacturer knows, and the moon is steadily counting down. You have felt this exact physics yourself, bending a paperclip back and forth until it snaps without warning. The moon bends every seal in the colony, slowly, on a 2-week rhythm, toward that same sudden break. And the third poison is the vacuum itself, working alongside the raw ultraviolet light. Together, they attack the soft materials, the polymers, the gaskets, the rubber O-rings that seal one pressurized space from the killing emptiness. In open vacuum, under that unfiltered light, these materials grow brittle, crack, and crumble far faster than they ever would in the gentle air of Earth. 3 poisons: radiation, temperature, vacuum, all patient, all permanent, and every time one of them wins, the colony faces the same grim choice. When something breaks on the moon, there are only 3 roads, and none of them is easy. Repair it, if you have the parts, the tools, and the skill. Manufacture the replacement yourself, on site, from whatever raw material you can process, or do without, and accept that the colony now runs at reduced capacity, one system weaker, one margin thinner, until you find another way. There is no fourth option, no hardware store, no overnight delivery, no specialist who drives out to fix it. The nearest replacement part that isn't already on the moon sits 250,000 miles away and cannot arrive for months. So every failure becomes a small emergency, and the work of fixing them never ends. A colony is not a place you build once and then live in. It is a machine you must repair forever, or die inside. And nothing shows this more sharply than the single most personal machine of all, the suit. Think about what a spacesuit truly is. It is not clothing. It is a personal spacecraft wrapped around one human body. Its own pressure vessel, its own air supply, its own temperature control, holding back the vacuum with a few millimeters of fabric. And the suits that walked the Apollo astronauts across the moon were miracles, but they were built for hours, a handful of brief excursions and then home. No one designed them to be worn again and again, year after year, in a place where the dust and the cold never relent. The new generation is far better. For the coming Artemis missions, a company called Axiom Space has built a next-generation suit, refining a NASA design, even bringing in the fashion house Prada to engineer the outer layers. It offers dramatically improved mobility, letting an astronaut kneel and bend and reach in ways the stiff Apollo suits never allowed, and it can support a spacewalk of 8 hours or more, a genuine leap forward. But even the finest suit is still a machine standing in the harshest environment there is. The dust still abrades it. The vacuum and ultraviolet still degrade it. The thermal cycling still fatigues it. A suit worn for a few missions is one thing. A colony would need suits that survive hundreds of cycles, hundreds of trips out into that killing environment and back, and that a colonist can repair in the field with their own hands when something tears. We have not built that suit yet. We are not close. And even when the suit holds, it fights the person wearing it in a way that surprises almost everyone. Here is something most people never think about. Fill a suit with pressurized gas to keep the astronaut alive, and the gloves stiffen. They inflate like a balloon, resisting every movement of the fingers. Simply closing your hand becomes work, like trying to make a fist inside an inflated rubber glove over and over for 8 straight hours. The toll this takes is real and documented. Wearing a pressurized glove, an astronaut's grip strength can drop to roughly half or 2/3 of normal, and the injuries are worse than sore hands. The single most common injury reported across decades of spacewalks is to the hands, including a condition where the fingernail slowly detaches from the nail bed entirely, from the constant pressure of pushing against the glove's fingertips. About half of NASA's spacewalking astronauts have suffered some form of hand injury. Half. Now picture doing delicate, precise work in that glove, connecting a fine cable, turning a small screw, handling a fragile instrument. Precision work outside is genuinely brutally difficult when your hands are trapped in stiff, pressurized shells that fight you with every motion and grow more exhausted by the hour. The moon does not just endanger the worker, it sabotages the work itself, which raises a question that has quietly divided the people planning all of this. If sending a human outside is so dangerous, so exhausting, so damaging, why send one at all? Why not let the robots do it? This is a real and unsettled debate. On one side, the case for robots is strong. A machine feels no fatigue, suffers no fingernail injuries, doesn't breathe, doesn't panic, and can be sacrificed to a task too risky for a person. Lean hard on robots, this side argues, and keep the fragile humans safe inside. On the other side, robots remain clumsy at improvisation, and the messy, unpredictable work of keeping a colony alive is full of exactly the surprises that human hands and human judgment still handle best. A stuck valve, an unexpected break, a repair no one planned for. How much to trust the machines and how much to risk the people is a balance no one has settled, and getting it wrong in either direction costs either lives or the mission itself. But whichever does the work, it has to move across the surface, and moving across the moon hides its own quiet gauntlet of problems. To reach anything beyond walking distance, a distant ice deposit, a science site, a sunlit ridge, a colony needs vehicles. Pressurized rovers, essentially small mobile habitats on wheels, holding breathable air inside so a crew can drive for days across the surface without a suit, then step out only when they arrive. Rolling lifeboats extending the colony's reach. But driving on the moon means solving problems Earth solved centuries ago and then forgot it ever had. Consider navigation. On Earth, your phone knows exactly where you are because a network of satellites, the system we call GPS, blankets the whole planet in positioning signals. The moon has no such thing. No GPS. No street signs, no maps, no familiar landmarks. Just grey, repetitive terrain where one ridge looks like the next. To find your way at all, an entirely new navigation infrastructure has to be built from nothing, satellite by satellite, before a rover can safely know where it is. Space agencies are already designing exactly this, networks with names like Lunar and a planned constellation to cover the poles. But none of it exists on the moon yet. Until it does, crossing the surface means crossing a world with no map, and every wheel that turns, every motor that spins, does so against that clinging, abrasive dust we met before, the electrostatic glass that migrates into every moving part. Each traverse grinds the machinery a little more, wearing bearings and seals in a place where a replacement is months away. The moon charges a toll on every mile, and it is paid in wear. But there is one thing the moon does not take from a colony, and it turns out to matter more than almost anything. Here is a rare mercy in this whole grim accounting. The moon is close. A radio signal, traveling at the speed of light, crosses the distance between the Earth and the moon in about 1.25 seconds. A delay barely longer than the natural pause in an ordinary conversation. Round trip, a message and its reply take only about 2.5 seconds. which means a colonist can actually talk with Earth, hear a familiar voice answer back almost at once, hold something close to a real conversation with the people they left behind. That may sound small. It is not. Consider the alternative. On Mars, that same signal takes anywhere from 3 to 22 minutes each way. So, a conversation means speaking into the void and waiting the better part of an hour for a reply. There is no talking with home from Mars. There is only leaving messages. But from the Moon, home is still reachable, still responsive, still there in near real time. In the crushing isolation we saw threaten the human mind, that thread of near-live contact is a genuine lifeline. The difference between being far away and being truly cut off. And yet even this mercy has a catch, hidden in the geography we keep returning to. The very place the colony most wants to be, the South Pole with its ice and its peaks of light, is a place where Earth barely rises above the horizon, if at all. From deep in those polar craters and low terrain, a direct line to Earth may simply not exist, which means the colony cannot even reach home on its own. It needs relay satellites, spacecraft parked in lunar orbit to catch the signal from the surface and pass it along to Earth and back again. Without that orbiting relay, the lifeline of communication goes silent. Another piece of infrastructure that must be built and launched and maintained before the colony can so much as call for help. And underneath all of it runs a network the colony cannot live without. Internal lines carrying voice, video, and the readings from thousands upon thousands of sensors, everyone watching some vital sign of the habitat. This pressure, that temperature, this oxygen level, that battery charge. A colony is a body wired with nerves, and if the nerves go dark, it cannot feel its own failures coming. Which brings us to the deepest vulnerability of all, the one that ties every other thread together. For all its self-sufficiency, a colony still depends on ships from Earth, and those ships do not come when needed. They come only when the cold arithmetic of orbits allows, on specific launch windows, narrow openings when the Earth and Moon align favourably, that arrive on nature's schedule, not the colony's. Miss a manifest, forget a critical part, or lose a shipment to a failed launch, and you do not wait days, you wait months, until the next window opens and the next ship flies. Picture needing a single component to keep your air flowing, and knowing the earliest it can possibly arrive is a season away. On Earth you order it, and it comes tomorrow. On the Moon the supply line runs on a calendar written by orbital mechanics, indifferent to your emergency, and the ships themselves are not guaranteed to arrive at all. The record of robotic landers reaching the Moon in recent years is genuinely mixed. Some touch down successfully, others tip over, crash, or fall silent in the final moments of descent. Landing softly on the Moon remains, even now, a thing that fails as often as it succeeds. Every resupply is a gamble, so the entire lifeline, the parts, the food, the fresh equipment, hangs on something far more fragile than any weld or seal. It hangs on the will of nations and companies back on Earth to keep paying, keep launching, keep caring, year after year, decade after decade. And here the accumulation snaps into focus. Self-sufficiency is not a luxury. It is not a goal for someday. It is survival insurance. The only hedge against a supply line that can be cut by a failed launch, a lost mission, or a change of heart in a government 250,000 miles away. And here is the final turn, the one that makes all of this real. The first humans to arrive would not walk into a finished colony. They would arrive to a construction site, habitats pre-deployed by robots, sent ahead and assembled, or half-assembled, by machines whose landing record we just called a coin flip. Not a home, a rough shell, waiting, with much of the hardest and most dangerous work still to be done by the people just stepping off the ship, Think about who those first builders would be. Not settlers moving into a prepared house, pioneers learning brand new lethal skills, how to seal a habitat, repair a reactor, weld against vacuum, drive a world with no roads, while a clock ticks on every consumable they brought, the air and water and food draining steadily whether the work goes well or badly, learning as they go, failing sometimes, with no room to fail badly. We have now walked through every wall of this. The vacuum, the frozen water and the smelted air, the 2-week dark and the private sun of a reactor, the dust and the radiation, the thinning bones and the untested child, the closed loop and the sealed mind, and now the endless grinding labor of simply keeping it all from falling apart. And a strange realization begins to settle. Every one of these problems, taken alone, might be solvable. Humans are clever, we solve hard things, but they do not arrive alone. They arrive all at once, tangled together, each one leaning on the others. The power that makes the air, the water that shields from radiation, the machines that need the parts, that need the ships that need the will of people far away, which forces the real question, the one underneath the whole journey. Not can we survive any single one of these threats, but whether we can hold all of them back, together, forever, without the whole intricate structure ever failing at any single point. And to answer that, we have to stop looking at the engineering and start looking at the cost, the politics, and the hardest question of all, not whether we can live on the moon, but whether we ever truly will. We have spent this whole journey answering one question. Can we live on the moon? Wall by wall, hazard by hazard, we've watched humanity's cleverness rise to meet the vacuum, the cold, the dust, the dark, and the answer that emerges is a cautious, astonishing yes. Not easily, not safely, but yes, it is in principle possible, which is exactly why we now have to face a different question, a harder one, not can we, but will we, because those are not the same question at all, and the gap between them is where most great human dreams quietly go to die. We know this because we have already done the impossible once, and then walked away from it. More than 50 years ago, human beings walked on the moon, not with today's computers or materials or reusable rockets, but with technology so primitive that your phone holds more computing power than the ship that carried them. It stands as perhaps the greatest technical achievement in human history. And then we stopped. For over 5 decades, no human went back. The boot prints sat undisturbed in the dust, and we turned away. Why? Not because we forgot how, because of what it cost. And here is a number that explains everything that came after. At the height of the moon race, the United States was pouring more than 4% of its entire federal budget into the space program. 4% of everything a superpower spent, funneled toward the moon. Think of what that means. Not 4% of some science budget, but 4 cents of every tax dollar the nation spent on anything at all. It was a sprint fueled by fear, a Cold War race against a rival, sustained by national pride and terror of coming second. And when the race was won, the fear evaporated, and so did the money. Today, that same space agency runs on roughly half of 1% of the budget, a fraction of what Apollo commanded. We did not lose the ability to go, we lost the will to pay. That is the ghost haunting every moon colony ever dreamed. Not, is it possible, but will anyone keep paying for it long after the excitement fades? And a colony is a bill that never stops arriving. We have a measure of what permanent presence in space actually costs, and it is sobering. The International Space Station, a structure orbiting just a few hundred miles overhead, in the easiest to reach patch of space there is the single most expensive object humanity has ever built. Its price tag runs to roughly $150 billion. And that is the cheap option, a station in low orbit, resupplied constantly, never more than a few hours from home. A colony on the moon would be vastly harder and vastly more expensive than that. And it would not be a one-time purchase. It would be a permanent line item, an open-ended commitment to keep launching, keep resupplying, keep funding, year after year, decade after decade, for a place that may never turn a profit and never fully pay its own way. Every single year, someone, some government, some company, some coalition would have to choose again to keep the money flowing, which raises the question that decides whether any of this is real. Why? Why would anyone pay that staggering, unending bill? What could possibly be worth it? There are, when you strip it down, only a handful of answers, and each one is contested. The first is science. The moon is an extraordinary laboratory, an ancient, undisturbed record of the solar system's history, and its far side is the quietest place in the inner solar system, shielded from Earth's radio noise, a perfect ear for listening to the deep universe. But science alone has almost never justified a cost this vast. It is a reason to visit. It has rarely been reason enough to stay. The second is resources, the dream of lunar wealth. That water at the poles, split into rocket fuel, turning the moon into a filling station for the rest of the solar system. Rare materials in the soil, perhaps someday an exotic fuel for future fusion reactors that barely exists on Earth. But every one of these runs into the same brutal wall. It is astronomically expensive to extract anything on the moon, and even more expensive to ship it anywhere. Whether lunar mining will ever actually turn a profit is right now genuinely unknown. It may be a gold mine. It may be a mirage. No one can yet say. The third reason is the boldest: survival. The idea that a species confined to a single planet is a species with a single point of failure. One asteroid, one catastrophe, one very bad day from extinction. Becoming multiplanetary, this argument goes, is a form of cosmic insurance for humanity itself. It is a genuinely profound idea. It is also, for now, more philosophy than policy, a reason that inspires, but has never yet loosened a treasury's purse strings. And the fourth reason is the oldest, and quietly the most powerful of them all. Prestige, power, being first. Strip away the poetry, and this may be the force that actually puts humans on the moon to stay. Not the pursuit of knowledge or wealth or survival, but the ancient primal drive of nations to plant a flag where rivals have not, and to be seen doing it. It was a race that first took us there, and it is a race that is taking us back, because we are right now in a new one, and it is no longer a two-horse contest. Consider what has happened in just the last few years, all of it real, all of it recent. In 2024, China landed a spacecraft on the far side of the moon, the hidden hemisphere that never faces Earth, and brought samples home, the first nation ever to do so. A feat the United States has never attempted. In 2026, American astronauts flew around the moon for the first time in over half a century, and the program to land them has already been reshuffled and delayed, the first surface landing now pushed toward the end of this decade. And running beneath it all is that race we saw earlier, the scramble to plant a nuclear reactor at the South Pole, driven by an open fear written into official policy that whoever gets there first might fence off the best ground and lock everyone else out. Two great powers and their partners converging on the same few miles of frozen, sunlit rock. This is the engine. Whether we admit it or not, geopolitical competition may be the only force reliable enough and stubborn enough to sustain the impossible cost of staying. We may go back to the moon for the noblest reasons we can name, but we may stay for the oldest one there is, and that leads to the most dangerous gap of all, because the rules meant to govern that ground were written for a different age. Back in 1967, at the height of the first space race, the world signed a foundational agreement, the Outer Space Treaty, and its core principle was beautiful in its simplicity. No nation may claim territory on the moon. Space was to belong to no one and to everyone. The moon was declared, in effect, the common inheritance of all humankind. But that treaty was written for a world of flags and footprints, of brief visits, not permanent bases and industrial mining, and it left enormous questions unanswered. If you cannot own the land, can you own what you dig out of it? If a company extracts water or minerals from lunar soil, whose are they? Can you build a base and declare a safety zone around it that others must not enter? A keep-out region that is, in every way that matters, a territorial claim by another name. A later agreement, in 1979, tried to close these gaps, to declare the moon's resources the shared heritage of all humanity, to be governed collectively. And almost no one who mattered signed it. No major spacefaring nation ratified it. It stands today as a near-dead letter, a road not taken. So we are moving toward the most contested real estate in human history, with no clear, agreed, enforceable law about who can take what. Individual nations are writing their own frameworks, forming their own coalitions, drawing their own lines. And here is the danger laid bare. Two rival powers, racing for the same sunlit peaks and the same frozen craters, with no shared rulebook to divide them. That is not a recipe for a peaceful frontier. That is a recipe for exactly the kind of conflict the original treaty was written to prevent, now playing out 250,000 miles from any court that could settle it. And if we imagine that a colony, once planted, would surely endure, history offers a quiet, humbling warning. 1,000 years ago, the Norse, the Vikings, did something remarkable. They sailed into the brutal North Atlantic and built a lasting settlement on Greenland, a harsh and distant land at the edge of their known world. It was not a visit. Thousands of people lived there, farmed there, raised children and buried their dead there for nearly 500 years. They even pushed onward and touched the shores of North America, centuries before Columbus. And then they vanished. The climate turned colder. The trade that sustained them dried up. The supply lines from home grew thin and thinner and finally broke. And the colony, established, populated, enduring for half a millennium, died out completely. The survivors, if any, sailed home or perished. The settlement was simply abandoned, swallowed back by the ice. Sit with that, because it is the whole story in miniature. A determined people, a hard-won foothold in a hostile place, 5 centuries of survival, and still, when the support from home faltered and the environment turned, the colony did not adapt or hold on. It ended. Being established is not the same as being permanent. History is full of settlements that were founded with hope and then quietly given up. The moon offers no promise of being any different, and every reason to think it would be harder. So where does this leave us? Standing, honestly, between 2 very different tomorrows. In one future, this all works. The reactors hum through the long night. The ice yields its water. The regolith gives up its air and its metal. The domes fill with crops. The caves fill with people. And the colony slowly, painfully, learns to stand on its own until one day a child is born on the moon who calls it not a mission, but home. Humanity becomes, for the first time, a species of more than one world. And everything we have described in this journey becomes the founding hardship of a new branch of human history. The way the first brutal winters are remembered by every people who ever settled anywhere. In the other future, we go, We plant the flag, we prove it can be done, and then the money runs out, or the rivalry cools, or a disaster steals the will, and slowly, like Apollo before it, the whole enterprise winds down. The last crew climbs aboard the last ship, the lights in the buried habitat go dark, and the moon returns to the silence it has kept for 4 billion years, holding our abandoned bootprints and our empty domes with the same vast indifference it has always shown. Which future we get will not be decided by the vacuum, or the radiation, or the dust. We have shown, across this entire journey, that human cleverness can answer every one of those. It will be decided by something far less certain than physics, by whether we choose to, and keep choosing to, long after the cameras look away. And so we return, at the very end, to where we began, to the thin wall of air pressing gently on your shoulders right now, and the ground holding you at exactly the strength your bones were built for, and the magnetic field turning aside a sky full of radiation you will never see, and the water and the soil and the breathable air, all of it, everywhere, all at once, and all of it free. That was the quiet truth threaded through every single hazard in this story. Every horror of the moon is simply the absence of a gift Earth gives us without our asking, and without our thanks. The moon is not cruel. Cruelty requires caring, and the moon does not care. It is simply a world that offers nothing, no air, no warmth, no water, no shield, no mercy, and demands that every single thing a human needs be dragged there or wrung from the dead rock by endless labor, and then defended forever against a universe that is always, patiently, trying to take it back. We spent this whole journey learning what it would take to survive a place that gives nothing, and in doing so, we learned what our own world has been giving us silently, every second of our lives, a gift so total and so constant that we built entire civilizations on top of it without once looking down to see it. Perhaps that is the real reason to go to the moon, not for the science or the metals or the flag, but because standing on a dead world, sealed inside a fragile wall with the void pressing in on every side, is the only way a human being could ever finally, fully understand the living one they came from. The moon may or may not become our second home, but it has always been the clearest mirror we will ever have, showing us, in its vast and silent emptiness, exactly how rare and how precious and how impossibly generous the first home truly is. We spent this whole journey walking away from home, across 250,000 miles of nothing, just to stand on a dead world and look back. And maybe that was the point all along. Because the moon never wanted to hurt us. It can't. It has no cold intention, no cruelty, no malice waiting in the dark. It simply gives nothing, no air, no water, no warmth, no shield, and asks us to survive on that. But turn around. Look at the world you came from, the air that finds you without asking, the gravity that has held every step you've ever taken, the quiet, endless generosity of a planet that has never once sent you a bill for staying alive. The moon is indifferent, and in its indifference it taught us the only thing indifference can, what it feels like to be, instead, completely cared for. Earth doesn't just let us live here. It gives us everything, freely, the way only love ever does. Thank you for making this long journey with me. If it moved something in you, a like and a subscribe are how you tell me to keep going. Rest well tonight. You're already exactly where you belong. Good night.